let's proceed to the mesh current analysis. Mesh current analysis, or loop analysis, is sometimes called Maxwell's circulating current method, and it is quite similar to the branch current method. The similarities between the both of them is that they both use Kirchhoff's voltage law and Ohm's law to identify unknown currents on the circuit. The differences between the both of them is that on the mesh current analysis, it does not use Kirchhoff's current law. Now here, we have an example circuit. We do not need to label each of the branch currents. Instead, we need to label the loops as the circulating currents. The first step on the mesh current analysis is we need to identify the loops on the circuit. So here we have two loops which we will call current number 1 and current number 2. The next step is we need to identify the polarities on the circuit. So first, on loop number 1, this will become a positive and this will become a negative since this is the formulation of the voltage number 1. And this will become a positive since on voltage number 1, it ended on the positive side. So we will start on the positive side on resistor number 1 and end on the negative. The same rule also applies on resistor number 3 since it is on the same loop. So this will become positive side and on the negative side. Since regarding the rule, it will be also applied on loop number 2. This is the positive side and this is the negative side. So this will naturally become the positive one and the negative. The next step is we need to formulate the equation on each of the loops. On loop number 1, since my loop is going clockwise direction, we will first start on voltage number 1. Voltage number 1 is positive. Then the next part is resistor number 1 multiplied to current number 1. And it is negative since it ended on the negative side. Then on resistor number 3, since my loop on resistor current number 1 and current number 2 is going downwards, hence it will become a negative. So here we have formulated the first equation on loop number 1. So on loop number 2, we will start on voltage number 2. Since my loop here is going counterclockwise, it will become a positive. So on resistor number 2 multiplied to current number 2, here will become the equation. And it will become a negative since it ended on the negative side. Also, since the direction of my loop is going downwards, it will also become a negative. So here, we already formulated the equation on loop number 2. Now, using these two equations, we can formulate or solve for the value of current number 1 and current number 2. Now, the next part we'll have an example or numerical example for mesh analysis. For another example, let us consider this circuit. In this circuit, we have 3 loops. First, this closed path. Second, and third. In every loop, there are circulating current, and we will name it. In this first loop is I1, I2, and I3. Given these 3 loops, we could be able to have 3 equations, and we can use KVL or Ohm's law in solving this kind of circuit. Let's consider loop 1. Our equation at loop 1 is
20 volts minus 5 kilo ohms times the circulating current, which is I1, minus 7 kilo ohm times the circulating current I1 minus I2. I1 and I2 is the circulating current across 7 kilo ohm resistor, and it is minus because the flow of the current of I1 is going down while I2 is going up. Minus 500 ohms times the circulating current I1 and equated to 0. The simplified equation of this is 12,500 I1 minus 7,000 I2 equals 20. And this equation is our equation 1. Doing the same process for loop 2, our equation is 7,000 I1 minus 3,600 I2 minus 400 IT equals to 0, and it is our equation 2. Doing again the process for loop 3, our equation is this, and the simplified equation is 400 I2 minus 4,120 I3 equals negative 40. And it is our equation 3. Solving equation 1, 2, and 3 simultaneously, we could be able to determine the circulating current I1, I2, and I3, which is, for I1, it is equals to negative 0.013 amperes. For I2, negative 0.026 amperes. And for I3, this equals to 7.18 milliamperes. We obtain a negative value of the current because the right flow of the current of I1 and I2 is opposite of the assumed current we set before.